Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome back. We were discussing till now shock tubes and various effects in shock tube due to viscous effects or contact surface tailoring, etc. We will come back to shock tubes today after some time. Today's class is supposed to be going towards high speed experimental facilities. Okay. And before going there, I just wanted to talk a little bit about yesterday's class. I was using some particular x versus time plot for these expansions and shocks, which is uncommon in class. Okay. So just to get used to it, I will give an exercise where I will give you the standard bookish x versus t curves for it, okay, in the exercise. I will also give this one as an exercise again, so that you get comfortable with both in one shot. Okay. One special exercise on that I will give for that last class. Okay. Now we will look at high speed wind tunnels. Of course, our course is only going to be dealing with compressible flows. So we are thinking about compressibility. So I am going to say Mach number high is good. So I am going to think about only tunnels where Mach number is more than 0.3, and I am not worrying about Mach numbers less than 0.3, where we will start neglecting Mach number effects. We are not going to talk about those cases here. Okay. This Mach number greater than 0.3 we dealt with in the very first few classes. We will not talk about it, why it is so, etc. now. Okay. Anyways, first thing we want to decide, do we need a tunnel to do the experiment? Okay. Of course, we can think about taking an aircraft, going at supersonic speeds, and then figuring out that the aircraft may not withstand it. That is dangerous. Instead, we will like to do this as an experiment and then figure out that it may experience this much level of forces, and then design your structure for that kind of forces that the aircraft will withstand. That is a better way of doing things. So I would say it is needed. Now when we are doing the tests, there will be typically so many limitations, because we cannot imitate nature the exact way. Okay. So what happens is, we will typically have limitations in this particular field in high speed wind tunnels. Typically limitation will come from time of operation. Okay. If you think about time of operation as a main parameter, I can think about tunnels that operate continuously versus tunnels that are intermittent, that is, it operates only for some time and then it has to stop, and then again I can start again and run for some more time, that kind of tunnels. Okay, that is intermittent tunnels. First we will just look at the distinction. The main problem will be the power requirement. I am putting this double line P for power. I will not use this power so much anyways. It is going to be of the order of half rho E square times some area of cross section of the test section or so. Okay. This is the kind of force required multiplied by the velocity. This is just a force times velocity kind of explanation for power. This is just order of magnitude wise, it will be correct, it will not be exact. I am just going to talk about this is going of the order of u power 3. Okay. If it is u power 3 and I am thinking about very high speeds, it is going to go as cubic function, it is going to be enormous power. Okay. When I go for very high velocities, the power keeps on increasing, and that is the main reason power requirements for these wind tunnels will become higher, that most of the labs cannot supply that high level powers for long times. So what we do is we store the power and then we deliver it in one shot till the power is lasting. After that we again start accumulating power and then deliver it again. That is the main option. Okay. If I think about continuous facilities, I have to keep on giving it continuously at this power rate, which is not going to be easy to deliver this much of energy per second. That is too high. So typically we will see only intermittent high speed wind tunnels. Okay. We do not see continuous wind tunnels ever. Okay. Of course, I have to say that there are a few where government funding is so high that they have made continuous wind tunnels, they have a separate power station powering it. Okay. and there are some closed circuit supersonic tunnels where the exit flow after the test section is again recirculated into the inlet, and that kind of closed circuit tunnels exist, but not very common. Common ones or most often will always be only intermittent tunnels. Okay. Now, when I look at intermittent tunnels, there are several types. Blow down type, I will come back to the intermediate one later, and then I have in draft type, and I have pressure vacuum type. Pressure vacuum type. I have these three types of intermittent tunnels. Okay. We will look at each one of them. The main idea of these tunnels is primarily I have a test section where I am going to put some model of interest, and I want to have flow that is of a particular Mach number going past it with the particular pressure and temperature conditions for that model. Okay. If that is the case, what I have to do in general, if this is my test section, I want to have a constant area duct so that things are simple enough, nothing changes, and I am going to put some model inside. Let us say this is my model and I am holding it somehow. We won't worry about this right now, we will come back to models in tunnels after this class. Okay. So, I am going to just look at this and I am going to say I need to have some particular Mach number at a particular pressure and temperature going past this. That is the main requirement of any wind tunnel. Okay. Now, I am going to say how do I do this? I need to provide a particular pressure ratio across it. Okay. So, the way I am going to think about giving a pressure ratio across this is to either, basically I need to have high pressure here and low pressure here. I can either keep this open to atmosphere and make this extremely low pressures, or keep the outside as the exit as atmospheric pressure and make this pressure extremely high compared to that. All that matters is just I need to provide very high pressure difference. Delta P needed for this should be provided. That is not enough. I need to have the particular area ratio such that for that mass flow rate it can achieve the correct Mach number. Okay. These are the requirements. So, now if I go look at blow down facility, as the name suggests, it is just blowing out in one shot and the pressure goes down and it stops working. The way it works, I have a high pressure chamber, from which I have an outlet and it has one on off valve, and then typically it will have some control valve to control the pressure of the flow that is coming out. Settling chamber, if there is any fluctuations in pressure or velocity, all those will be lessened if it is going through this one. Why? The area change is so high that for this mass flow rate the velocity inside here will be very, very low, and for very low velocities turbulence does not exist. So, it is almost laminarized and the velocities are so low, disturbances will die down very fast. Okay. And after that I am going to accelerate it and take it through to my test section with an appropriate nozzle in here to get appropriate Mach numbers. If I want a supersonic Mach number, then I will use a convergent divergent nozzle. If I want only a subsonic, say Mach 0.7, sorry. If I use Mach 0.7, I just need a convergent duct probably. I can still use a convergent divergent nozzle with appropriate pressures such that I will get even for this subsonic conditions at the exit. You know nozzle flow problem, I do not need to discuss that anymore, but typically people use CD nozzles for getting supersonic Mach numbers, and after this I just have to think about a diffuser at the end this is going to be my test section. Okay, things are not really drawn to scale, but typically test settling chamber is bigger than the test section. That's how it will be. Diffuser can keep on going forever. It will be typically very long. I'm not drawing it really long because it just occupies the board. Okay. So it's something like this. Typically they think about exiting to atmosphere, but starting from very high pressure. I am providing the high pressure exiting to atmospheric pressure in this side. That is a blow down facility. Okay. In this, test section size and the Mach number decides the throat, and the pressure at which I operate will decide the mass flow rate through this. And based on the mass flow rate and the settling chamber pressure, the P naught, that will decide the run time of this facility, right. This high pressure tank will have some initial pressure, say it is 100 bar, and I want to operate with the settling chamber pressure of 10 bar, then this can keep on supplying this pressure of 10 bar here only up to a point where this becomes 10 bar. After that I cannot use this anymore. That is where this is an intermittent facility. Okay, I have pumped in so much energy into this, pressurizing this chamber. Okay, I stored so much energy, P naught, right, pressure energy in the gas. I have stored so much of energy, and finally it is let in through this whole region. P naught I am controlling based on this valve or a regulator, typically it is a regulator in this point. Okay. And from here, based on the mass flow rate, if the mass flow rate is very high, so much mass is removed from here, which means the pressure will drop faster. Okay. So I will have lesser run time if my mass flow rate is higher. So the test section size decides based on A by A star here, test section size decides the A star, and P naught is something I want to set based on the pressure in the test section I want. Based on Mach number and pressure in the test section, I can set my P naught. With this setting, P naught and A star, I am going to get a particular mass flow rate. Of course, I am going to assume T naught is same as whatever is inside here. Okay. And based on that, I will get my mass flow rate. That is what is deciding how fast am I depleting the pressure inside here, number of molecules going out of this. So it becomes an intermittent facility based on that. Okay. So now I will go for in-draft tunnel immediately after this, so that you can immediately see it as a very nice contrast. This is the other version, that is I am again having the similar to this one. There is a nozzle here and there is a diffuser here, and in the middle there is a test section. Here again I have a nozzle here, diffuser here, and in the middle there is test section. This whole unit is the basic supersonic tunnel. Now how am I providing the pressure difference across this is what matters. You know, we discussed this double throat nozzle. What is really happening here is a double throat nozzle. That is all it is. Basically it is a single CD nozzle which is again having a bump here, so it becomes a double throat nozzle. We will come back to that discussion again. Anyways, now the way I am doing here, I am going to say atmospheric pressure here, and I am going to have some grids to decrease turbulence. Okay. You would have seen such things in fluid mechanics when we are discussing low speed tunnels. Typically they have this kind of intakes to decrease disturbances outside. And they will have this kind of intake, very nice intake, to have better efficiency, intake efficiency. Okay. So here P naught is fixed value, which is our atmospheric pressure. Typically P naught will not change much in this case. Here P naught may keep on changing if my regulator is not working very well, blow down facility. Okay. Here P naught is decided by the regulator. If my regulator is not very good, and I am drawing too much of mass flow, then the regulator may not keep up very well, and so the P naught may slowly change, or it may be going up and down depending on whether it is moving continuously or in steps. Okay. But that is not the case here. P naught is a fixed value. Atmosphere, very difficult to change atmospheric pressure for us. Okay. It is going to be the same. Over the time scales of interest, atmospheric pressure does not change at all. Okay. And the main thing here is the pressure drop is given by low pressure on the other end. I am going to have a huge vacuum pump which is going to evacuate this chamber. Finally, when I open this valve, there will be suction from here into this whole thing, and that creates the flow field. And now you should know what matters is for this to get a shock somewhere here. If I say I want supersonic flow, I do not need to have full supersonic flow all through till the tank. All I care about is the shock sits here, then the flow was subsonic here, went to choking condition here, became supersonic, went to slightly less supersonic, and then has a shock subsonic here. That is enough for my operation, because what matters for me is only the test section region. Same thing goes here. We will never operate with fully supersonic flow coming out. We will typically have a shock somewhere here. That is the condition we will operate with. Okay. And what are the advantages and disadvantages of these two? This is called an in-draft tunnel, because now I am having flow from outside coming in, and that is what is creating the flow field. Okay. These are called in-draft tunnels. Now, advantages and disadvantages. Vacuum tanks, very safe, it is not going to explode at all. Its maximum pressure difference from inside to outside is only 1 atmosphere. That is a good thing about vacuum tanks. While high pressure tanks may explode, there is a danger of the whole thing exploding, but this is very easy to get, because most industries have high pressure tanks. So, very easy to get a high pressure tank than a vacuum tank. Okay. But of course, you can use this tank for a vacuum, it may not withstand very well, that is all. Okay. Much more easy to get a high pressure tank. Why? Most of the industries work with high pressures. Okay. So, that is one thing we have to think about. What decides the runtime of both these tunnels? We already discussed this. It is the mass flow rate, the pressure in the tank versus what we need, and the size of the tank, volume of the tank, how much really the mass is present inside. If there is so much mass inside, say 100 kilos of mass, and I am running it 1 kilogram per second, I can run it only for 100 seconds. That is assuming I can evacuate completely, that is also not possible. When it goes from 100 bar to 10 bar, I cannot use it anymore. So, I can use only 90 kilograms. Okay. So, like that is volume of this tank also matters. Okay. Same thing goes here. When there is so much mass flow coming here, that is going to fill this tank, which is decreasing the pressure downstream. So, the delta P across is decreasing. So, eventually there will be a point where the shock moves more upstream, can happen that way, that is also a possibility. Okay. Now, there is one more problem with this blow down facility, where if I have really high pressure so that I will get lot of run time, I am going to have the problem of, if I have a mass flow rate going through this, there is depletion of mass here, so the gas here is going to expand. When it is expanding, what is going to happen? It is going to get colder. If it is getting colder, it is going to take up heat from here inside. Okay, it is going to take up heat from here into this point. So, it is not really sitting at particular condition, it has to start cooling things. Okay. That is one way of looking at it. So, my walls and the tubes are all going to be a little colder, this is called the Joule-Thomson effect, I believe. Okay. So, that will start happening, that is one thing, and if the pipes are very small in size, you will have more effect of it. I have had a case where I had icing on top of my stainless steel tubes, okay. And of course, my data was all wrong, because my T naught, what I assumed was room temperature, okay. But that is not the case if there is icing on top of the tubes. Okay. So, you should be careful about that also in there. Okay. If you look at cost wise, which is easier, cost wise it so happens that blow down facilities are easier, and that is why most common supersonic tunnels are blow down facilities. Okay. This one, it looks like it is very simple, but vacuum pumps are not very cheap. Okay. And to maintain this pressure, you have to have really good vacuum, so that you will have flow for long enough time. Okay. That is the next thing. Now, if I look at the pressure vacuum type supersonic tunnels. Actually, I just have to say high speed tunnels, nozzle can be anything still, it need not be supersonic alone. What I am going to do is, I am going to put a high pressure tank for the high pressure here and low pressure tank, the vacuum tank for this side. So, this immediately tells me that I am going to have much higher capacity for this flow to happen. Typically what they do is, I can set very high pressure difference across here, that the Mach number that I want to experience will be higher. Typically they use pressure vacuum tunnel for Mach numbers above 5 or so. Okay. That will look like this. I have a high pressure tank, I have similar design, I have a regulator, I have a settling chamber, and then I have my nozzle which is going to produce whatever flow. I will typically draw it a bigger size test section for this, the A by A star bigger, to emphasize that it is much higher Mach number condition, and everything else is similar. I am going to have another system with control here and then a vacuum tank. I will have a vacuum tank on this side. Okay. So, if we think about this, this is going to have both the positives and negatives of each of the previous ones we discussed. Okay. That is going to be a special case in here. I now need to have a high pressure tank and a vacuum tank. So, I need to have vacuum pumps, which is again expensive, and this is safety hazard, all that together. That is the bad points. Good point is, now I can set very high pressure on the upstream side and very low pressure on the low downstream side, and eventually I will get lot higher capacity possible. Okay. Those are the advantages and disadvantages of these systems in here. Okay. If you want really no disturbances in your P naught values, you should go for in-draft tunnels, which is a little more expensive. Okay. That is one special case. Otherwise, you can think about blow down facilities which are quick and easy to make. Okay. And one more thing, if I use high pressure tank to supply, my air which I am pumping into this for use inside this flow may have some oil vapors from the compressor. Okay, your air may smell different if you go smell it, if you ever see that facility. Okay. Then that could be a problem. If I have an in-draft facility, that is not a problem, because now I am taking fresh air from atmosphere around me. Okay. So, now the next thing we want to talk about is operation of a supersonic facility. Now I won't worry about what is giving the pressure difference, I will just look at the basic supersonic facility, that is up to here, settling chamber to the diffuser alone. How I set the pressure difference across there, I won't talk about anymore. Okay. This is your pressure vacuum facility, actually I already wrote it, pressure vacuum facility. Now I want to look at only the basic supersonic facility, which is, I have some settling chamber, from there I am having a nozzle followed by a straight section, which is my test section. This is my nozzle, and after that I am having a diffuser, and somehow I am setting pressure difference across this. Okay, we know how to set it, we have 3 different ways of doing this. And if I want to think about putting a model inside, I am going to put some model inside and hold it somehow. We will come to what models can be inside, etc., some other class. Okay. What do we have to talk about? A1 star and A2 star. Okay. And let us say I want some particular Mach number in the test section, M. Okay. So, we already discussed the problem of a CD nozzle with another bump in the nozzle, okay, where we said that if I want this not to choke, I need to have a condition such that this mass flow rate coming out through this, which is choked, must be able to go through this one, and we said that the area should be more than a critical value. We said A2 star by A1 star, the critical value is equal to P naught 1 by P naught 2 for that Mach number shock. Okay. This was our condition we came, and we said that if the area is more than this value, then it will not choke, okay, then it is safer. So typically if you are designing a supersonic tunnel, now you have to think about this area more than this particular value. This is the minimum area that is possible. Do not ever keep the minimum value, because in this analysis we did not take into account P naught drop due to friction. If you have long test section, your friction effect will be much more. Okay. Typically to avoid this problem, what they do is they make this nozzle such that it is almost flat parallel towards the end, and they put the model in here itself. Then the nozzle itself, nozzle end point itself becomes your test section. That also people do for decreasing cost, of course. Okay. People do that, but a more clear experiment should be when I have this straight section where I want to make sure the Mach number is constant everywhere. That is better. Okay, but of course my assumption is not true if I say friction is not here. Friction is present. If I take into account friction present, what should I do? As I go here, I am going to have P naught loss, and so my Mach number will go towards m equal to 1. If I started with m equal to 3 here, say my nozzle is m equal to 3, it may end up with m equal to 2 at the end if my nozzle is too long. In that situation, what should you do? Since it is supersonic flow, I will use area divergence. I will make my walls expand a little more, so that my Mach number from here to here will be constant. Okay. That is the next special case. Okay. And you can exactly calculate how much should be the area divergence. So, for that particular Mach number, for the particular friction factor F and the hydraulic diameter D for your test section, etc. You can calculate and put that value, and you can measure the Mach number, and it will be almost the constant, whatever you expected. Okay. That is possible to do. Now of course I have to talk about starting of this tunnel. How does the tunnel start? I am going to apply P naught and I am going to apply a PB. We will apply it such that we know that the flow will start very nicely. So we will go through, look at our nozzle flow problem again. What will we say? As P naught increases keeping PB constant, we are going to have fully subsonic flow all through initially, and this is the smallest area point. So this is the first point which gets choked. After that it will be choked and subsonic fully. After some time there will be a shock that forms, which people call the starting shock. It forms somewhere, as in it starts from the throat and keeps moving downstream as I increase my P naught. If I keep doing this, this shock keeps on moving more and more downstream. You go to this point next, and this will be gone, and eventually it will go past your test section, and then it will go sit here. If I increase my P naught some more, from here, it has to go to a higher area than this. So the next higher area is sitting past this point. So the shock may go there, which is higher than this particular level. And from there, if I keep on increasing P naught, it may go and sit even further downstream. Okay. That is also going to happen. Now if I think about tunnel starting, this is the actual process. I just went through a full starting of a tunnel. When the shock crossed my model, immediately I have a supersonic flow here. Okay. Why can't I just keep my shock sitting here? If there is any perturbation, it will jump in. I do not want that situation. Okay. So we will push it to the other side where it is extremely stable in the divergence section. We already talked about this. Shock is stable in the divergence section. So it will typically we will put the shock in the divergence section and we will leave it there. Okay. Now if I think about how much energy am I wasting on this, am I efficient enough if I put my shock here? Most likely no, because I am having much more higher P naught than what is required for minimum operation. For minimum operation, all I need is maybe the shock should have gone from here to here. But think about it, I have given much more than that, which means I am wasting more energy. Okay. Where is the energy going finally? It is going as a higher velocity jet at the exit. I am wasting the energy in the form of kinetic energy of the gas. Okay. So I do not want that to happen. What will I do next? I will decrease my P naught, maybe I will come here, and that is efficient enough, yes. But now I see If I decrease my P naught further, the shock is not going to jump to the test section, it will still sit here because the area can be even lesser, it is still in the divergence portion of the diffuser. So what will happen, this is your diffuser, right, I did not mark it, the second nozzle is your diffuser. So I can now make it operate with shock somewhere here, just downstream of my second throat. If I keep it operating here, still the shock is sitting in a divergence section, if there is small perturbation nothing will happen, it will not jump in, it will still stay there, it is stable enough there, so it stays there. If I give a huge perturbation, of course it is going to jump in and immediately it will go and sit with some other area similar to that, which will happen probably somewhere here. If I give a huge disturbance, it is going to jump here, then now I have to increase my P naught very high so that it pushes the shock all the way back to this point, till that time I have to operate. So now they will think about some safe operation point where it will never jump into the test section. So they will tell that, okay, the minimum needed is this value of P naught, I will operate say 10 psi above it, something like that. They will operate slightly more pressure than that, so that they are having a safety margin somewhere. This is typically the way a supersonic tunnel works. Okay. They will keep it such that the shock starts and goes that side. If you are not worried about too much of runtime, we will not worry about bringing it back, because while you are thinking about bringing it back and closing a valve, you are wasting so much of mass flow rate, now your runtime becomes even lesser. If I want to worry about runtime being long enough, then I will do this quickly, I will go test section from here, the shock from here jumps out of test section into the diffuser divergent, and I will pull it back to just downstream of throat, and I will keep it there. Now I will run it at most efficient situation for how much ever time possible. Should I always worry about this particular thing? Not always. Okay. Why? By the time I adjust this, if all my mass flow rate is gone from the tank, it is useless to do this adjustment, instead I will get some time without adjusting it. Okay. That is typically the trade off people use, and I have seen tunnels where there is no second throat also, where they just put a straight section and a divergent portion. I have seen tunnels like that also, where I am not really worried about efficiency, I am just going to push the shock into there and take data inside. This is actually an extended nozzle if you think about it, just a CD nozzle, just a straight portion in the CD nozzle and then a divergent portion again, that is all I am having. Even that will work. I have a straight section where I know my Mach number is going to be constant, and I will use my model in there, that is good enough. In fact, in our GD lab in IITM we have one such facility for Mach 2, where we do not use the second throat in there all the time. Okay. So now if I think about delta T of running, if I have a second throat, then my P naught will be lesser. If I bring my shock to this point, P naught will be lesser and my runtime increases. Why? My mass flow rate is decided by the P naught. If my mass flow rate is less, I am not evacuating all the molecules from my original high pressure tank, so I will get runtime a little longer. Or if it is in draft tunnel, I am not going to fill that downstream vacuum tank with lot of molecules if mass flow rate is lesser, so I get higher runtime. Okay. So typically you have to think about mass flow rate really, but people really talk about P naught and area of the test section and the Mach number. Actually if you think about all that, it just comes down to m dot inside here, m dot and the tank supply pressure and the tank volume, those are the primary variables for our runtime calculations. Okay. Now we will go back to our shock tubes again. This is one way of creating high energy flows. Next we will go for, I will just draw the end of the shock tube. This is just the low pressure section of my shock tube. We know that if I extend it that side, I will have a high pressure section, diaphragm and the low pressure section, everything, whatever we did last class. Okay. Now we know that in a shock tube, when a shock is coming this way, behind it the flow is typically supersonic. Of course I can make it subsonic also, when the pressure difference P4 by P1 is not very high, then it may be subsonic flow also behind it, but typically we will have a case where it is supersonic flow behind the shock. Then when the shock is coming here, flow behind it is m greater than 1 and all this flow is having exactly the same Mach number, neglecting viscosity, okay, neglecting friction, we discussed that last time anyway. If I have such a situation, now if I put a small diaphragm here, actually not small diaphragm, I will put a thin diaphragm here which can hold low pressure difference across this, but not the shock post shock pressure. Then what will happen when the shock reaches here, immediately the diaphragm experiences huge pressure difference across here and the diaphragm ruptures. Typically people use thin plastic sheets there. If I use thin plastic sheet, one side is very high pressure, other side very low pressure, it just gives up, it cannot stand there, it will be like a balloon bursting. Okay. And immediately downstream of it, if I put a divergent duct, what will happen? I have flow behind it m greater than 1 and I am putting a divergent duct, I can expand the flow further to even higher Mach numbers, and typically if I curve it such that it becomes parallel for some time, I can put my model here and say that now my flow experienced by this is going to be that high Mach number based on the area ratio. You guys know how to calculate this already. So you can find that Mach number here and that particular Mach number will be the flow situation here. For all this to happen, of course you still have to think about what should be the pressure here. It should be low enough. Okay. If you do not have low enough pressure, things are not going to happen right. So typically what they do is, in this kind of a facility, they will have the model in a vacuum tank, okay, and the end of the shock tube is now going to have a expansion nozzle, expanding nozzle. So this whole flow facility now together is called a shock expansion tunnel. Okay, basically it is a shock tube and now the flow behind the shock is expanded further to get to whatever Mach number you want. Typically they use this kind of facilities for really high Mach numbers, something like hypersonic flows, 7, we have a hypersonic flow facility where we can go all the way up to 25 Mach. Okay, of course it just depends on what area ratio I use. Okay, beyond some point I will not believe the data because it may become non-continuum. Okay. Then I have to think about it, I can make a nozzle for 100 also Mach number, but at that point the pressures are so low that it may become non-continuum. Then I have to worry about, is my data really valid? Okay. We will not worry about that right now. Okay. This is one particular facility, shock expansion tunnel is basically at the end of the shock tube. I do not have a solid wall but a thin membrane which will break when the shock comes and reaches there. Okay, and of course for it not to break, initially I should have had the same low pressure this side, so that the pressure across the diaphragm is 0, there are no difference across the diaphragm. Okay. That is what we should have had. Now I will draw one more case. This is again the low pressure section of the shock tube, high pressure section is somewhere to the left, and this time I do something different. I have a small hole in the end wall and put a CD nozzle from there, and again I put a membrane here, and again I maintain two different pressures similar to the other one. There it was just expansion, here it is compression, what do I call it, CD nozzle, convergent and divergent, okay, in here. So I have a shock that is coming here. Now I designed this diaphragm a little stronger. I am going to say it will not break for the post shock pressure here, but it will break for the reflected shock post shock pressure, the P5 it will break. I will put it a little stronger so that it will not break for P2 and this value, but it will break for P5 and this value. So the shock comes this way and then it goes back, and the shock goes back reflected, that pressure is too high for this, and so what I have essentially done is created a very high pressure, very high temperature gas, stagnant gas here, right. We discussed this at the end of shock tube, this stagnant gas, compressed gas, stagnant gas, and essentially there is a nozzle, CD nozzle. Basically it is like our test section. Any supersonic flow, I have created the high pressure here and I am setting a low pressure based on a vacuum tank on the other side, and basically I have a flow inside this. This is my vacuum tank. My model will be sitting somewhere here, let us say, something like this. Model will be sitting inside here. Basically, I am now providing high pressure and low pressure for the flow to happen. Similar principle as everything else, just that the high pressure and low pressure, high pressure is created by the shock tube. That is the only special thing here. Low pressure is still the vacuum tank. Now, what is the main drawback of this facility compared to the other ones which we used high pressure tanks? What is that? Pressure? In this one pressure can change. That is not the main thing, I think. Why do you say pressure will change? Because of the shock. Okay, I want to come to that. After some time the pressure changes, because the shock may reflect at the contact surface and come back, or expansion may come back after reflection at the contact surface. Because of this, your run time comes down. Okay, that is the main difference. In intermittent facilities with pressure tanks, the run times will be of the order of few seconds, few tens of seconds probably. Okay, our facilities are operating up to 20 seconds or 25 seconds long. Okay. Here the times will be of the order of few microseconds, a few hundreds of microseconds, maximum 1 millisecond or so, that kind of time scales. Okay, this is extremely small times. And what decides these times of the run for a shock tube? For run times here, it is not related to the mass flow rate through this nozzle anymore, because after some time I do not experience the same P naught and T naught. So, it has nothing to do with mass flow rate anymore. Of course, there is a special case where the mass flow rate is so high that this gas is depleted, that may happen. That is not the most important thing typically. Typically it will be the pressure and temperature P5 T5 here, it may not be the same anymore. After some time the reflected shock will interact with the contact surface and come back as a shock or expansion and disturb this gas again. That is typically the case. So, if I have to think about wait, I am losing track of what I wanted to say, I already lost the track. Okay, if I want to think about the run time, of this particular shock tunnel, this is actually shock expansion tunnel, this is actually a reflected shock tunnel. If I have to think about run time of a reflected shock tunnel and or a shock expansion tunnel, how will I increase this? First thing I can do is tailoring of the shock, tailoring of the contact surface when the reflected shock, I can do that. Second thing is I can make the expansion, if I tailored, then the only thing that disturbs it to decrease the delta T will be the expansion wave that goes all the way to the other corner in the high pressure section and comes back, right, we did that last class. So, when it comes back, it will come back if the length is very short. If the length is very long, if my tube, my whole shock tube is really long, then I will have that much longer run times. Okay. But even then I am not going to have few seconds or so, it will still be in milliseconds only, it will never be going to seconds of time of run times. Okay. I have seen photos of long shock tubes, you can also see on the web, it's everything is all available on the web. Okay. There are big research facilities where these shock tunnels will run half a kilometer or so full length, that kind of things. It is possible to make something like, okay, where you will get much higher run time, probably few milliseconds, maybe 5 milliseconds or so, that kind of times. Okay. So, length of the low pressure section to high pressure section, those also matter. Okay. Those are all important parameters. If I want to do the test in a particular gas, then what matters is how much time is the contact surface going to take to come and reach this corner. Once the contact surface comes and reaches this point, it is no more the same gas that is flowing through this, it will be something different. So, that also cuts down my run time. There is one more thing I have to worry about if I have special gases that I am testing. Okay, need not always be the case. Okay. As of now, we have discussed so many high flow rate facilities, high Mach number facilities, which are like blow down facilities. I told there could be a closed circuit facility for supersonic flow, but I did not discuss that really. Okay. We have blow down facility, in draft facility, pressure vacuum facility, and then we said shock tube based facilities, reflected shock tunnel or a shock expansion tunnel. Okay, we discussed it the other way. Okay. These are different facilities that are possible. Okay. People use all of these. Okay. In fact, in GD lab we have the same shock tube, but it can have this nozzle at the end of it, or it can have this nozzle at the end of it going to the same tank, vacuum tank, and that will change the what type of tunnel it is. Okay. Either it is shock expansion tunnel or a reflected shock tunnel, you just decide based on that. And of course, you have to use appropriate diaphragms for those. The diaphragm we use for this is just a thin cellophane sheet, and this one is 2 layers of cellophane tape. That is the kind of things we need to use, just a little thicker, but it breaks for higher pressure typically. Whatever packing tape we use, that kind of tapes are good enough for this as a diaphragm. The next set of things that we have to discuss are not pressure based. Okay. Of course, whatever we discussed here, this and the shock tubes, shock tube based wind tunnels, they are all pressure difference giving energy for the flow. Okay. There are other facilities where it can be a mechanical piston giving driving the flow, that is one possibility, giving energy to the flow, or it can be combustion driven, or it can be electrical heating driven. But of course, eventually it is all going to create the pressure difference across the nozzle for the flow to happen. Okay. How am I creating the pressure difference is the main change here. Here blow down facility, I create a high pressure tank and the atmospheric pressure. In draft tunnel I am going to say atmospheric pressure and a vacuum tank. Here it is high pressure and vacuum tank. In shock tube I am creating that high pressure high temperature gas, and that is being used here. Okay. The next set of things we need to discuss will have pistons moving and combustion driven and electrical heating driven. Okay. I do not think I have time to start any of those, so I will stop for today. Any other questions you have? See you people next class.